71. Novocaine, which is C13H21O2N2Cl, is the salt of the base procaine and hydrochloric acid. The ionization constant for procaine is 7 times 10 to the negative 6th. Is a solution of Novocaine acidic or basic? And then what are the H3O plus concentrations, the OH minus, and the pH of a 2.0% solution by mass of Novocaine, assuming that the density of the solution is 1.0 grams per mole? Okay, so let's answer the first question, right? Is the solution of Novocaine acidic or basic? So let's talk about this. This is Novocaine, so C13, H21, O2, N2, and Cl. Now, they did say that this was a salt of the base procaine and hydrochloric acid. Now, procaine, off the top of my head, I have no idea what procaine looks like, but I know what hydrochloric acid looks like. And hydrochloric acid is HCl, and that's kind of color clashing, so we will say HCl. Now, when we're going to talk about whether this is acidic or basic, we have to have one cut, right? Because when we break up our salt, we have to have one positive ion and one negative ion. Now, if one of them came from hydrochloric acid, here's the Cl. So the Cl should have been by itself. So here, I would say the break is. Because if I break this up, this kind of makes sense. Cl would be by itself, and C13H21O2N2, which I guess this would have to be procaine, right? That's a minus sign. Now, just know that when we're dealing with, solutions that are deemed acidic or basic, we always talk about aqueous solutions. And aqueous solutions just mean that we have water. But if I just rearrange this, it's easier to think of water as one hydronium, which is H+, and one hydroxide, which is OH-. The H+, opposites attract. The H+ will always go with the Cl-, and the OH- goes with the plus. This should be a plus right here. I don't know why I put a negative there. So hydroxide always goes with the first positive, and the hydronium goes with the negative. So that's why this makes sense, because it would be HCl, which is hydrochloric acid. And then we have the procaine, which would be C13H21O2N2, and then we'll just add an OH to it. Now we're going to discuss these compounds. Let's start with HCl. Is HCl one of my 6 strong acids or 6 strong bases? And yeah, it's one of my 6 strong acids, right? HCl right here, one of my strong acids. So I'm just going to say that this is a strong acid. Now, anytime that you do have a strong acid, just know that the conjugate is so weak that it's just easier to call it neutral. So HCl is a strong acid, which means that this would have to be a neutral conjugate. Let me just move this out of the way. Whoop. And since it's neutral, I could basically cancel this out because it has no acidity nor basicity to it. Now we just do the same thing over here. Is this on my list of 6 strong bases? No, right? These are just group 1s and group 2 ions, not this huge C13H21O2N2. So this would be classified as a weak base. If it's not a strong base, it's classified as a weak base. And now we're over here. But just know that weak bases, the conjugates would still be slightly weak, but it has the acid word. Remember, bases turn into conjugate acids, acids turn into conjugate bases. But it's acidic nonetheless. So since you have a weak base, the conjugate that we have is slightly weak, but it's acidic nonetheless. I can't cancel this one out because it actually has acidic properties. So now you just say to yourself, okay, if I have an acid component coming together with a neutral component, that would just make the whole Novocaine acidic. So we answered the first part. So here is the answer to number 1. Novocaine is acidic. Okay, so that's this part. Now, pause the video because I'm going to get rid of all this at the bottom because we need a lot more space here. So just pause the video if you want any of these tips and tricks, but I'm getting rid of it. Bye-bye. There you go. Okie dokie. And, let's see. Let's see. If I want to set myself up, I'm going to, actually, I'll get rid of this. Actually, this I can get rid of because this was the neutral component. I'll get rid of this, the H2O. And all we basically just need is we need this component of the Novocaine. When we're doing ice tables later down the road, just know that you only care about what is actually acidic or basic. And we just learned that this was acidic, right? Okay, so this was acidic. This is Novocaine. And remember, the base, they told us that the base was procaine. Okay. So now let's just get rid of this. And this is the only two things that I need for right now. Okay, let's progress with the question. Now, they did tell us that the ionization constant for procaine is 7 times 10 to the negative 6th. Now, what I'm going to do is I'm going to actually just say this. Okay, cool. And this is basic. So if they did state that it was base, and we found out that it was basic, this ionization constant, even though it just said ionization constant, this has to be a Kb value. So the Kb value is 7 times 10 to the negative 6th. But now if we just read on, they're asking for the hydronium, the hydroxide, the pH of Novocaine. They're not asking for procaine. So at some point, we have to convert the Kb into the Ka. And how do we do that? Well, there's one formula, right? We've seen this before. Kw equals Kb times Ka. If we want to solve for Kb, or actually we want to solve for Ka, we could just divide Kb on both sides, right? So I'm just going to do that right now, just to kind of make it easier on myself. So we'll take Kw and divide it by Kb, and this will equal the Ka value. Okay, well, they told us the Kb value is 7 times 10 to the negative 6th, and they didn't tell me what temperature we're at, but I'm assuming that we're at room temperature because that's the only Kw that they would expect you to memorize. The Kw at room temp is 1.0 times 10 to the negative 14th. So that's the first thing we're going to do. We're going to take the Kw, divide it by that Kb to find out what that Ka value is. 1.0 times 10 to the negative 14th divided by 7 times 10 to the negative 6th. Calc keys out. So 1 times 10 to the negative 14th divided by 7 times 10 to the negative 6th. And I guess a couple of sig figs here. We'll say 1.43 because technically these are not the answers that we want, so we don't give the correct sig figs. So I'm just going to erase this. And I'm going to say that this is now 1.43. 10 to the negative 9th. Okay. That step is done. Now we're moving on. Let's see. Now we want to write out an equation. So now in this case, we did all that we can with the procaine. Keep in mind that the question was asking for just Novocaine. So I'm going to get rid of all of this. So pause the video if you need to. But this is going, and this is going as well. Okay. So I'm just going to move this up. Now, since we have a Ka value for the Novocaine, let's write out a balance equation. So let's just say C12, or actually C13H21O2N2 positive. Now, this is a weak acid, so it's at equilibrium. And the good thing with weak acids or acids in general is that you do not need to add plus H2O. You can, but you don't have to. All you have to do, remember, is that you just drop one of your hydrogens. In this case, all the hydrogens are right here. So it kind of makes it easy. So instead of 21, you're going to bump it down to 20. And that would be your conjugate base. So you have C13H21O2. Hold on, let me just make that a little better. O2N2 plus that one hydrogen that you bumped is the hydronium, which is H+. Just know that all charges, this one was a +1, this should be a +2. Should it be a +2? Actually, no, it should be neutral. Because +1 minus 1 is 0. But just know that that's also going to be aqueous as well. So all of these are going to be aqueous. So aqueous all around. And we're going to use that in our Ka expression. All right, so we're getting there. Now, if we're going to set up an ice table, we need to know initial concentrations. But the only thing that they told me was that I had a 2.0% solution by mass of the Novocaine. That's not good enough. Remember, when we do the ice table, and maybe I will actually do that just so that I can show you what I'm talking about. So when we do the ice table, ICE, and maybe this we can ICE and bring this a little bit down. Okay, that's beautiful. Remember, only molarity is allowed in here. And just to set ourselves up, right? Molarity, remember, is something divided by something else. It's the moles divided by the liters, right? And specifically, it's the moles of the solute divided by the liters of solution. Let's see if we could get these numbers by just a 2% solution by mass. Now, there is a formula way back in like Gen Chem 1 that we learned about percent by mass, and that's this formula right here. Percent mass is always the grams of the solute divided by the grams of the solution times 100. Now, the only thing that they told me was that it was a 2.0% mass. So I'm just going to get rid of this percent and say that, hey, I have 2.0%. But now I have to come up with the ratio that will satisfy this number. Now, this times by 100 is standard, right? That's in the formula. So if you wanted to get rid of this 100, you would divide by 100. And look here, this is in the denominator. So if I put 100 down here, that will cancel out the 100s. So we're getting somewhere. So in this case, the solution, there's 100 grams. So if the 100s cancel out, in theory, 2 would equal how many grams? It's the same number. So this would actually be 2. And now we have our solute information and our solution information. Right now we know that we have 2 grams of the solute, so we have to convert that into moles. So 2.0 grams of the solute, which is the Novocaine, right? So maybe I'll just put Novocaine. I have to convert that into moles. And maybe I'll just move this up a little bit. Novocaine. And then we have 100 grams of the solution, which I have to turn into liters. So I have to do 2 conversions. Now I think the solution one is easier because they told us that the density of the solution is 1.0 grams per mil. So maybe I'll just hold off here for a little bit. I'll bring this up and we will work with the 100 grams of solution. Now if I want to go from a mass, because that's what a gram is, I want to go from a mass to a volume. What's that formula? It's the density formula, D equals M divided by V. we know the mass. The mass is 100 grams. And we know the density. They told us that it was 1 gram per mil, right? So if I just needed to solve for volume, what I would do is I would just take these and just rearrange this formula so that volume is equal to mass divided by density. 1.0 grams per mil. And I can do this because gram will cancel out with gram. But the thing here is that this volume will be equal in mils because that's the volume of the density. So 100 divided by 1 is 100. So maybe if I just move this over, we have 100 mils. But in order to use molarity, I need to put it in liters. So we could just make a conversion factor. Milliliters on the bottom, liters up top. 1 liter is equal to 1,000 mils. Or you can just take the decimal, move it over 3 times to the left. So it'd be 0.1, right? 0.1 liter. And I'm just going to write that over here. So let's just get rid of this. This now becomes 0.100. And maybe I'll put the L here for liter. Okay, halfway there. I'm going to stop the video if you need to just write down this density stuff for the solution, but it's going because we need to do the conversion for grams to moles. So, bye-bye. Okay, so now let's convert from 2 grams of Novocaine to moles of Novocaine. So grams to moles, we know how to do that. 2.0 grams of Novocaine. And if I can, write out what the Novocaine is. Now, just keep in mind that this was the only portion of Novocaine that is actually the acidic portion that we write for the balanced equation. But Novocaine is including that chlorine. So when we're doing grams to moles, I have to include that chlorine there. So it'd be C13H21O2N2Cl. Times by that ratio, grams of the Novocaine on the bottom, C13H21O2N2Cl, and moles of C13H21O2N2Cl goes up on top. Mole to gram conversion is always the periodic table. 1 mole equals whatever the mass is on the periodic table. So periodic table's out, and let's see what we get. So I got 13 carbons, so 12.01 times 13. Then I got 21 hydrogens. Okay, then I got 2 oxygens, so 2 times 16. Then I got 2 nitrogens, so 2 times 14.01. And then I got 1 chlorine, and the chlorine is 35.45. So I get 272.768. Grams cancel out with grams. We're going to do 2 divided by that number. And I try not to round as much as I can because this is not the final answer. So it's 0.007332, we'll say. And that's moles. And that's now going to go on the top. So I can just erase this. And maybe I'll put 0.007332. And that's moles, right? Now I could finally find the molarity. Moles divided by liters. So 0.007332 divided by 0.1. And I get a molarity that's equal to 0.07332. Finally, there we go. So now pause the video because everything else is going except for that ice table. We're finally ready to proceed. Whew, this one is crazy. And maybe I'll just put this up here, I guess. So that's what we're starting with. Remember, I stands for initial, and the initial Novocaine was what we just found, 0.07332. 0.07332. And I can get rid of this now. Did they state that I had any of these ions starting off? No, they just said that we had 2% of the Novocaine. So I gotta assume, okay, I had nothing here and I had nothing here. C stands for change. Well, if you start off with nothing, you could only go up from there. So we know that this side, the product side, has to be addition, and the reactant side has to be subtraction. Do we know by how much? Not at the moment. So minus X, and plus X. Equilibrium is when you combine all of them together, initial and change. So 0.07332 minus X is 0.07332 minus X. 0 plus X is just X, and 0 plus X is just X. Now we're going to use this information to plug in with our Ka values. Okie dokie. So let's just start from left to right. Ka, if we had to write an equation, just to show you, it would be products divided by reactants, right? So it would be C13H21O2N2 times H plus, and divide that by the original Novocaine, C13H21O2N2. And that's a positive. So let's actually plug in those numbers. So I got these two on the top, one on the bottom, and we actually know the Ka value. So I'm actually going to extend this. I'm actually going to extend this a little bit out here. The Ka value is 1.43 times 10 to the negative 9th. This was X, this is X. And now here's the thing, guys. Since this Ka value is so small, that means that at equilibrium, you will have mostly reactants. But here's the thing. If you started off with mostly reactants, and you're going to end with mostly reactants, is this minus change a big one, or is it a small one? It's a small one. It's so small that this change probably is negligible, which means that we can get away with it in terms of math. So I can just say, as far as math, I'm going to pretend that this minus X doesn't exist. I don't want to do the quadratic formula. I don't want to do more work than I have to, right? So I'm just going to put the 0.07332. I can't get rid of these X values because then I won't have a variable to solve for. Now let's cross multiply. So now we're just going to solve for X like we normally do. Crisscross these up. So 1.43 1.43 times 10 to the negative 9th times 0.07332 is roughly we'll say 1.0485 times 10 to the negative 10th, and that equals X squared. X times X is X squared. So if you want to solve for X, just do the square root. That gets rid of this, right? So I'm just going to square root 1. Oh boy. I'm going to square root 1.0485 times 10 to the negative 10th. And I get an X value of 1.0. I guess, is this one of the answers? Actually, this is one of the answers. So maybe I'll give 2 sig figs. So 1.0 times 10 to the negative 5th. And that's molarity. That is the X value for H+. Keep in mind that H+ is the same as H3O+. So since they're asking for H3O+, H+ is the same. And that's what X equals. 1.0 times 10 to the negative 5th. So let's, actually, I think I can move this over because I kind of still want to show this. And I think, let's get rid of this molarity. Pause if you need to write it down, but the molarity is going. I'm going to put this all the way over here. And now I'm just going to say, okay, H+ is the same as H3O+. And for those answers, we got 1.0 times 10 to the negative fifth molarity. So we have 1 out of the 3 answers. Okay. Now, we have to find out the OH minus concentration and the pH. Well, the pH is pretty easy. Remember the formula pH equals the negative log of the H plus concentration. That's why we like to find out H plus first, because H goes with H. So since I now know the H plus concentration, I can just plug it in to solve for the pH. So just pause the video, because I'm just going to get rid of this math down here, if you need to copy it. And I'm just going to move this down over here, just to show you that, H goes with H. So pH equals negative log of 1.0 times 10 to the negative fifth. Okay? So negative log of 1.0 times 10 to the negative fifth. It's basically 5. So we have that answer. pH equals, and we'll say 5.0. I think it's 5.00 if we actually do sig figs, but does anyone care? No. So 5 on the dot. So it's pretty acidic, less than 7. And now, for the last thing, is we have to figure out what the OH minus concentration is. But just remember, Kw equals the concentration of H plus times the concentration of OH minus, right? So it's H plus. Maybe I'll do these like little brackets here just to show that it's multiplication. So if we want to solve for OH minus, all we would have to do is just divide by the H plus on both sides. So I'll just show that real quick. So this is coming down. And then we have a nice little formula here to figure out for the OH minus. And the same as before, the Kw is 1.0 times 10 to the negative 14th. The H plus is what we just found out, 1.0 times 10 to the negative fifth. So let's get to it. 1.0 times 10 to the negative 14th divided by the 1.0 times 10 to the negative fifth. And that just equals the OH minus. And then let's see what we get. 1 times 10 to the negative 14th. This is basically just subtracting the exponents, but I just like to do it in the calci. So we found it out. OH minus equals 1.0 times 10 to the negative 9th. And that's molarity. And those are your 3 answers, guys. Whew, this one was crazy. And this is the last part for hydrolysis of salts. So if we can get this one down, you're pretty good for this chapter. All right, we're moving on to, I think, polyprotic acids. So hang tight. And if you want to please help us out, press the subscribe button. Thank you so much. It just gets the word out there that this service exists. And I hope you guys are having a great day. Keep studying hard, and I'll see you later. Okay, bye-bye.